second lecture on Friday. So if you have questions, please stop. So we will start as follows. So we will consider a family of smooth projective varieties over a disk. So I will start locally, then I can go globally. And the idea will be to construct the parameter space for Hodge structures in a map that goes when you have a family like this. So the first point is that you have something called the Keresman lemma. And I'm already in a local situation. So this will be telling you that this total space of the family will be diffeomorphic to the central fiber times the disk. X is going to be the central fiber. So I can make this sufficiently small. And so what this is telling you is that if you have a family of algebraic varieties defined by a polynomial on some projective space, smooth, all these fibers will look the same if you look at the smooth structure. So in particular, topological invariance will be the same. In particular, the Betti numbers are going to be the same if you consider another fiber of this family and you compare it with the central fiber, right? And this is by definition, this is the dimension of the K homology group. Let's see coefficients. Let's see the same. So now we want to define some invariants that look at the algebraic structure, not only differentiable. And so we have the Hodge decomposition. That this is the composition of the cohomology into further subspaces. That it's some T plus Q equal K of some groups that can be computed with differential forms having P DCs and Q DC bar. And we have also a lemma that is, let's say, the analog of this Keresman lemma in this case. Let me call this invariance of the Hodge numbers. Well, rather of the consequence here. And this is going to tell you that when you deform this X, the central fiber, the Hodge numbers that are going to be the dimension of these subspaces are going to be constant, just like this statement. So let me just write them in the following way. BPQ of X, this is by definition the dimension of HPQ of X. And this is going to be the same as that one of the fiber that is close to X, right? Probably I should also. Sometimes I will denote this by X0. I have X0 in my notes. If I forget, I will see also X0. And so using this diffeomorphism, you can see the Hodge decomposition. You will have a Hodge decomposition for every T on the disk. And so using this diffeomorphism, we can actually see how these subspaces are varying inside the same vector space. So I will fix this X, and using this diffeomorphism, I will see how these vector spaces are varying. So for this, let me go into define the parameter space. So later we will want that the map that we are going to define is going to be holomorphic. So I need to define something called the Hodge filtration to obtain this. And we will define Fp of Hk of X. And this is going to be those part of the Hodge decomposition that have P prime bigger than P. K minus P prime X. So whenever you have a Hodge decomposition, you can define something like this, and you can also encode information in something of this type that is called filtration, and you can recover this Hodge decomposition, but I'm not doing this. So I will introduce more notation to encode the dimension of this. So this notation was to encode the dimension of the groups that I had. So now denote by small f p the dimension of this fp. And so I have this invariance of Hodge numbers. So I'm actually just making direct sum of this. So this will imply that if I vary this filtration, if I put some t here, this will have the same dimension. So I also I obtain some numbers that are not varying with t; they are fixed. So now this filtration is decreasing. So what is the meaning of this? That I have that f0 is going to be the whole hk. Then you use the node like this. But if I'm increasing the number here, it's going to be included in the one before.
But for the Hodge filtration, you want to write xt.
Yeah. Here, you mean?
Yeah.
Yes. This is just a definition to define, but I will define it for everyone. Yes. So yeah, here it doesn't really matter. It's and so I also want to denote the whole collection of these numbers, and I will denote that by f dot, and this is going to be fk minus 1 till f0. So this is small f, so those are the dimension. So definition, if I take for a complex vector space V, I will use the following notation. So the flag variety, I will denote it by FL. They will have the following information. I will have this collection of numbers, just like I denoted here. In the vector space that I will be considering, this will denote the set of nested subvarieties and I will consider subspaces of B satisfying looking like this. Sorry, reverse that. So they are included into one another, and F0 is going to be V, and with the correct dimension, with the dimension of F, capital F, P, V, small f p. So I'm constructing the moduli space of subspaces of B that are varying in this way and having the correct dimension. So an example is of course given by a family of these varieties that I'm constructing now. A whole space like that will turn out to be a complex variety. And if I want to justify this, we need to use some theory of elliptic operators, but we will actually get a C-infinity map in the following way. So this is going to be like the local period map. This is going to be defined from the disk to a flag variety like this, having the numbers associated with the central fiber, and in the space that they are varying is in the HK cohomology of the central fiber also. And the map is, you will map a point T to the filtration defined by the cohomology of the fiber HK. So I'm using a little bit here the notation. All of these should be seen inside X0. So if I wanted to be very precise, I need to twist by the inverse of the diffeomorphism given by the Hertzman lemma, but I'm omitting this to simplify the notation. And this PX is called the local period map associated with the family X. So actually the variation of Hodge structures turn out to be equivalent to having something called the period map, not the local, that I will describe at the end, but this is encoding how the variation of the Hodge structures are moving with the parameter T.
I'm sorry. So
yeah.
The way you define that there is a choice in the Hertzman lemma.
Yes, I'm omitting this just to simplify the notation, but you're right. I need to twist it so that this subspace can be seen inside this X0. Is that what you're saying? Yes, I'm omitting it just to simplify the notation, but you're right.
I was wondering whether it's canonical or not. So it should be canonical.
Probably you have to twist by something, but I'm not. Reducing this size. More questions? So now I want to compute the derivative of this map, and for this I need to see the tangent space of here. And actually, note that when you have this flag variety, this is contained in a product of Grassmannians that I will denote like this. So if k of b times Grassmannians of fk minus 1 till Grassmannian of f0. So I will actually just give you the formula for the tangent space of the Grassmannians. This is as follows. Proposition. Let me consider fi to be a point of the Grassmannians of dimension fi inside the vector space V, and then the tangent space at fi of these Grassmannians is going to be isomorphic to the homomorphisms of fi, capital Fi, to the quotient of V to this fi. So in particular, we will have that the tangent space at some filtration of this flag variety with these numbers. This is going to be inside the product. This will write in direct sum. And now let me state the main theorem. So these are the theorems. Repeats. So we have 3 points. In the first one, we'll say that the period map is holomorphic. So I was telling you that we obtained something C infinity here, but this is going to be actually holomorphic. The second one is that it's something that we call Griffith's transversality. So if you look at this first approximation of the derivative, it is telling you that it will land inside this whole vector space. In this Griffith transversality, it says the following: so the derivative of the period map that I will denote like Px star lands in so the following subspace. This is the direct sum of homomorphism of Fi, and it will only reduce by 1 here. So it will not land in the whole F, sorry, in the whole V, but just a smaller vector space. And so this will allow us to identify the derivative of the period mapping. At least in the graded part. So we have an induced map. So if we consider the graded part, let me just denote by F, not write everything. So this rigid transversality is telling you that F P plus 1 is going to go to Fp. So if I consider this graded part, this goes to 0, so I have actually something well defined. And this is a way of writing Hodge numbers. So using something called Dolbeau isomorphism, we see that this is going to be isomorphic. So the homology group K minus P of the forms of degree P, and this is going to increase the homology degree by 1 and decrease the form. So let me stop a little bit here so you can read the statement. And this product, this map, is the composition of the cap product so we have HK minus P, the P forms, and this goes K minus P plus 1 omega P times the tangent space of X, the cap product with eta, the Kodaira-Spencer class, and then we compose with the contraction map. So we have a P form. We take the value in a tangent vector, and then we go to a form of degree 1 minus. So we actually have a very explicit description of the derivative of this mapping. So I will be talking on Friday about infinitesimal methods in Hodge theory. So one of the part of infinitesimal methods is that you can really see what is happening with the derivative and use the properties. So Professor Biff is going to be talking tomorrow and on Thursday about properties of the period domain. So when you have a global family, you have curvature properties, and you can actually use this to deduce properties about the geometry of the family that you started with. So questions here?
So how the statement 3 is related to the statement 2 and 1? So
How the statement
you have an induced mapping.
statement 2 reduces this map.
Yes.
Why?
Why? Because
because
okay,
I
okay, I see.
have isomorphism. So the thing is that
If you take multiple,
this map to be well defined, I need this property, right? If not, this thing wouldn't go to 0 here. So so yes, I need to actually take a point in the tangent space, let's say at 0 of the, probably this is not a good notation, so vector. And this vector will induce a map like this. So this map is the map that I'm using here. So I'm fixing, let's say, a vector. Any other question? So let me just recall briefly the definition of the Kodaira-Spencer class, and I will sketch a very rough idea of the proof. So recall that the Kodaira, let me use the node KS, Kodaira-Spencer class is defined in the following way. So in the total space of the vibration, we have a exact sequence as follows. You have the tangent space of the central fiber, and this goes to the tangent space of the whole total space restricted to X, and you can also pull back the tangent space of the base, in this case the disk, let's say at 0, and also we restrict to the central fiber. So the Kodaira-Spencer class is defined as follows. You need to, we have a connecting morphism or map that goes from H0 of the pullback of the tangent space and goes to H1 of Tx. And we are in a disk, so we have only a so we need to pull back the vector field d and dt, and we send this by the connecting morphism, and this is going to be the class of the Kodaira-Spencer. So this is the class that we are doing the cup product with here. So this is given +1 on the cohomological degree, and it's tensoring with Tx. So this is coming from this. And to prove these two statements, we proceed as follows. So let me erase this. So sketch of the proof. So we need to consider a smooth section, be a smoothly varying section of Fi, Hk, once again we can find this by elliptic operator theorem. And the thing is that we need to argue and find infinity differential forms that represent this class. So actually we may find a form Vn. So let me just write the definition of this Fi. These are going to be now global forms on the total X, such that the restriction of the differential form, so each fiber, this represents E of t for all t. And then we just have to use the Cartan-Lie formula, and we will have these two properties. So now, using Cartan-Lie, so this is telling you that if we consider the derivative with respect with first with t bar of this smooth section, this is going to be the Lie derivative of the vector field t bar applied with 2 pi. Once again, I'm using the notation here because I'm using Kereson lemma. And Cartan-Lie formula will tell you that I need to take the derivative of this form phi that I found. I need to contract with the vector field given by t bar, and then I also need to take the derivative of the contraction first, and then the derivative. So if you look here, we are on Fi. So this phi will have at least I this set. And so when I contract with something that kills this set bar, I will still have in at least I this set. So let me just write it. Both terms have at least I these set terms, and thus this derivative will land in Fi hk of x0, and so it goes to 0 in the quotient in FHK. So I gave you the formula for the derivative of, for the tangent space at the Grassmannians, and that formula just was the homomorphisms from this space to this, but this is going to 0 if you take the derivative with respect with some anti-holomorphic vector fields. So this is the definition that the map is actually holomorphic. So this is the sketch of proof of the first point. And the second point is very similar. So you will have to take the derivative with respect now with t, not with t bar. And you can use the same formula. You just have to contract with this t. And so this will, instead of having i's big set, you will have I minus 1. And so this implies that you will actually land on this filtration using the same argument here. And now for the third part, there is also a similar argument. You will have to compute some Lie derivative, and you will have to explicit the Collider-Spencer that I told you. You need to pull back this vector field and then take v bar of this vector field, and knowing that this represents the Collider-Spencer class, you will identify the parts having the part living in fi minus 1, and you will find that they coincide. So once you have found this, using the Cartan-Lie formula will tell you that 1, 2, and 3 are true. Questions? So this ends the local part. I will just have a few more remarks on the global case. You can go to the beach if you have some. Can I erase here? So let me just write what I said. So we can define, let's say global, but we don't really use this terminology. A global period map. So now we will consider the same as before. Just I will change D by a quasi-projective variety. This is going to be a holomorphic family of projective varieties. Smooth projective. A submersion. Now we have this invariance of the Betti number, so we have that we can consider the higher direct image of C, and this is going to be a local system on T. I didn't say it, but T is quasi-projected now. Let's say smooth quasi-projected. So if we push forward this, C with arcade, we have a local system on T, and if we tensor with the structure shift of the base space, we obtain a flat vector bundle the Gauss-Manning connection, just deriving the base direction. And so this flat vector bundle will give a representation of the fundamental group. So HK gives a natural representation. This is rho, and it goes from the fundamental group of the base to the automorphisms of. I will still denote by x0 some central fiber. We'll have to choose a base point on P. And the thing is that this representation, this monodromy representation, is going to respect whatever information we have. So in this global setting, we will consider actually polarized family that I will introduce in a second. And this representation, we have to respect this polarization. So instead of having a local period map, we will have to make the quotient by the image of this representation, and then that will be the definition of the period domain after we restrict to some smaller subspace. So this is called the monodromy representation. And this is given by if you have a homology class that I'm representing as a cycle, and you have an element of the fundamental group, it's defined by parallel transport. Defined by parallel transport. So with this definition, if there exists an analytic line bundle, calligraphic L over X, such that the restriction of this line bundle to every fiber is ample for all T, then we say that the pair is a family of polarized variety. It's a family polarized. So now when you have a polarization, you have induced a pairing in the for a polarized family XL. If we have K that is smaller than N, that this is the dimension of the central fiber. So we have a pairing. This is not completely incorrect, but let me just define it like this to give you an idea. So this is going to be defined by integration over x, and these are cohomological classes, and then I take differential forms representing to this, and the restriction of the line bundle to x0 will give you an ample line bundle. Then you probably have to put a -1 here. It's not. And for phi I, these are going to be cohomological classes in HK. And the monodromy, this needs to preserve this pairing. So now we will define B to be so we actually want when I define the flag variety FL, this turns out to be quite big. So let me use a note like this. F dot is going to be F dot for this central fiber, and V is going to be HK. So you need to impose two conditions, because if the monodromy will respect this will give you two conditions that are known as the Riemann bilinear relations, and this needs to respect these conditions. So we actually can make this parameter space smaller, and these are the conditions that they need to satisfy. So I should probably put here the correct indices, because these are going to be some main objects that Professor Reddit is going to be talking over. For any non-zero psi in HPQ. Yeah. That's why I was telling that this is cheating actually, because this is not going to be actually positive if I don't. Yeah. I need to. Yeah. Omega is the Furniture class of this restriction. So omega is third class of L restricted to 0 with this notation.
Otherwise, you need to modify the pairing.
Yes. Just let me skip this for time, but yeah. You're right. Because otherwise that can be 0, and that's not going to define something. But so let me call gamma the subgroup of the automorphisms in HK x0 with the integer coefficients, preserving that pairing, and then it turns out that this gamma acts on this D, and we called this quotient the period domain. And we also have a period map. It's storing the global properties of this map. Is the third paper of Professor David. So he has 3 papers on these integrals of forms on complex variety. The first one is defining the period space. The second one is studying the local properties, like in the theorem that I gave you, it shows that it's holomorphic. And the third one is studying the global properties. So I'm not telling you much about the global properties. You are hearing about them tomorrow. So I think I will stop here.
Any questions?